Thank you, Lisa. Good morning, everyone. My name is Sakineh Chabi, and I am Assistant Professor of Mechanical Engineering at UNM. And it is a great pleasure to talk to you about our technology today. I am also the founder of Silicon Carbide nanosheet technology. And currently I have 3 researchers in my team working on this technology, Mr. Skylar Gillespie, Mr. Asim Khouri, and Mr. Asim Poudia. So far we raised 50,000 in internal funding. So why this technology is important? So basically, two-dimensional silicon carbide is really very important and have huge potentials because bulk silicon carbide is a very important material. As a wide band gap semiconducting material with high thermal stability, silicon carbide is a leading material for high power, high temperature, high frequency applications. For example, it enables fast charging of electric vehicle or even space electrification. However, the problem and the need is that current SiC technology is far from ideal. And also for the future technologies, we are moving towards smaller, thinner, more flexible devices. Such things cannot be achieved with bulk silicon carbide. And another thing is that because of its reduced thickness, two-dimensional silicon carbide will outperform bulk silicon carbide in several ways. For example, bulk silicon carbide has indirect band gap, meaning it has very poor luminescence and optical properties. But because of its atomic thickness, two-dimensional silicon carbide is direct band gap material with very strong optical properties. So it can enable applications, devices not currently possible with bulk silicon carbide, but at the same time allows us to take advantage of silicon carbide properties such as fast switching or, for example, used for harsh environments, because silicon carbide has excellent physical and chemical properties such as chemical stability, high temperature tolerance. And the application, while silicon carbide has very broad application, I am not going to talk about all these applications today. However, the biggest market is semiconductor devices, and we are going after 2 specific markets for now. One is light emitting diodes, and the other one is power electronics such as MOSFET transistor. As I mentioned earlier, bulk silicon carbide has very poor luminescence property. You cannot use it to make LED. If you use it, it will be very inefficient. But two-dimensional silicon carbide has direct band gap, strong luminescence. We are planning to use it for blue LEDs. When it comes to power electronics, even though silicon carbide has an edge over silicon, but it is far from ideal. For example, current challenges with silicon carbide MOSFET are how to improve or reduce power loss and how to improve the quality of materials. Our two-dimensional silicon carbide can solve both. Why? Because when we talk about two-dimensional silicon carbide, it has much reduced thickness. As such, it has much less resistance. It means improved charge mobility and better power efficiency. And in terms of material quality, the problem with bulk silicon carbide for power electronics is the coexistence of different polytypes. However, with two-dimensional silicon carbide, it doesn't have any polytype. It just has perfect hexagonal crystal structure. So the expectation is that two-dimensional silicon carbide will enable smaller, flexible, and more efficient, less expensive devices. I think I missed these slides. Yes, so what is, sorry about that. So basically, two-dimensional silicon carbide is a new form of silicon carbide. It is a single or a few layer form of silicon carbide. And what we did is that we made the world's first two-dimensional silicon carbide. We also have published patents, as you can see here, on two-dimensional silicon carbide. and in fact got published a few months ago. And this is a picture that you see here from flexible, transparent silicon carbide nanosheet. It is in fact the first structure because silicon carbide is a very brittle material. So we invented such a structure. And regarding the market for two-dimensional silicon carbide really has lots of opportunities when it comes to semiconductor devices. As you can see here, for example, one of the applications that we are going after is light emitting diode. As you can see from graph A, this market is growing at a rate of 81.5%. It is really huge. So we see lots of opportunities. And it isn't only LEDs. When we talk about wearable displays, you cannot use bulk materials for such ultra thin. By ultra thin, I am talking about nanometer level, not micrometer level, by using bulk materials. So we see lots of opportunities here. Or another thing here, graph B, show you the market for SiC power devices. By 2025, the global market will reach 2.5 billion. And here you can see some of our current results. Image A, B, C shows you optical microscope and then transmission electron microscope of our silicon carbide nanosheets. You can see how transparent and flexible they are. Image D shows the atomic structure of a graphene. As you can see here, this atomic structure is different than all existing silicon carbide. All existing silicon carbide have polytype like 6H or 4H. And the problem with many of these devices is the coexistence of this polytype 4H, 6H, but two-dimensional silicon carbide has perfect graphene-like hexagonal structure. And here from image F, you can see the thickness of some of our nanosheets is 2 angstrom. We are talking about angstrom level technologies by using such nanosheets. However, I should also mention that when we are talking about silicon carbide nanosheets technology, we are not limiting ourselves to monolayer or few layer. No, we are talking about anything around 1 nanometer or less. And image J and H show our result from photoluminescence. As you can see here, this image J, is achieved from only one single nanosheet. The thickness is less than 1 nanometer, and the weight we are talking about less than nanogram. Okay, with less than nanogram, you can see how strong the photoluminescence is, and of course, the emitted light is 2.58. It belongs to a blue light. So this confirms that our two-dimensional silicon carbide has a huge potential for blue LED and other luminescence devices. Also, since silicon carbide is a bio-friendly material, another application would be bioimaging. And current status of our technology, we are currently working on device fabrications. We haven't made any device yet. Our technology is really at its very early stage, but our results are very promising, and we also collaborate with local national labs on this technology. I plan to apply for some SBIR and STTR soon, and hopefully we will also get some venture capital fund or angel funds in near future. And also the big players, for example, in the country are Wolfspeed, or also known as CRI, but we hope to get such major players to license our market in the future. At the same time, we plan to submit multiple patents in the future so that we create a larger IP barrier for our technology. Thank you, and I would be happy to answer the question.
Thank you very much, Sakineh. And I'll open it up to our sharks for questions. John?
So how much time and how much money is it going to take to get to the first customer?
Here is the answer. Our silicon carbide nanotechnology has different applications, okay? So for example, one option that we have right now is that we can simply just sell silicon carbide nanosheets. with silicon, if we sell, for example, we just want to start with selling silicon carbide nanosheets, then I think we can, yes, we don't need that much of funding. Now, if I want to talk about, for example, power devices, or for example, LED devices, then the price would be around, for example, anywhere from 1 million to 5 million.
Thank you.
Okay, thank you. Other questions?
Yes. Your presentation, and maybe I don't know enough about this, but it reminded me of hearing, about graphene. And when, graphene has been this wonder material that has a lot of potential, and I can see the parallel with that nano thin silicon carbide. But when you go to prototyping, a lot of companies don't really know what to do with graphene. And so it slowed down the development so much. So I'm just wondering, you're talking about licensing to Intel and players like this. What are some of the key actual products that you think you need to develop so that you get the interest from those companies? Because just licensing it as just a material is very hard.
Thank you very much, Julia, for your question, because indeed, one of the biggest advantage for our two-dimensional silicon carbide over graphene or other this new material is that silicon carbide has well-established and mature market. For example, silicon carbide wafer exists. As such, two-dimensional silicon carbide can definitely benefit from such market. Then regarding your question, in fact, I've been in contact with some of those big industries. They want us to really make the device. They don't, unfortunately, they don't want to, for example, maybe I don't want to say they don't believe us at this stage, but they really want us to do every single thing and then tell them that exactly, see, for example, here we measure it. It is, for example, here the efficiency, we do exactly the same thing, and maybe then they will talk to us. Or some of them, they told me, okay, go and make wafer, 8-inch wafer. Of course, making 8-inch wafer with two-dimensional silicon carbide, it is not in my plan for now, because there are other challenges involved.
Okay. So how do you prioritize? How do you pick what to do first?
For example, we need to get all the data that we can, like, for example, I haven't got the charge mobility of this two-dimensional silicon carbide yet. Or for example, with LED, my plan is really that let's make it ourselves. I mean, we don't have other options, because I think that maybe it is not the best time to license our technology right now. Maybe it would be better that we make some progress so that it will put us in a better position when it comes to negotiation.
Okay, thank you. Matthias, do you have any questions for Sakineh?
Yes. How easy or how involved is it to produce these nanolayers? And second question, how chemically stable are these nanolayers when exposed to our atmosphere, including the traces of ozone, which we unfortunately see everywhere?
I just take note of your question so that I don't forget it. So the first question, thank you for your question, Matthias. The first question was about the fabrication, how easy it is. It is in fact complicated a little bit. For example, when it comes to graphene, it was easy. People just use Scotch tape to exfoliate it. Why? Because it has very weak bonding. But with silicon carbide, it is much more complicated because it is strong. But we know, we have the expertise. For us, it is extremely easy. But for others, if they want to repeat that, they would encounter lots of complexity. But in our case now, it is very easy for us. But for others, it is not easy. Why? Because there are lots of things, like, for example, which polytype you are going to start with, which, for example, and yes. And I think your other question was about the stability of these materials. In fact, that is excellent question because I forgot to cover it, that in fact, one of the biggest advantage of our technology over existing silicon carbide is that they are resistive toward oxidation. As I showed, for example, in one of my TM image, we showed the graphene-like structure. They are stable. We test their environmental stability against, of course, air, oxygen, and they showed excellent stability. They don't form SiO2 layer that easily. And that is another advantage for this over silicon carbide, because why we have this low, for example, charge mobility with silicon carbide materials such as 6H, because the silicon carbide gets oxidized easy, but we can solve this problem by using highly stable crystalline two-dimensional silicon carbide.
Maybe a follow-up question, if I may. You mentioned also IP protection, which you are going to pursue, patents. Will the patents include also the production of these nanolayers, where you seem to have an advantage over other groups?
In fact, the patent that we already published, it is all about the synthesis. It focuses on the fabrication. Yes, but the future patents, yes, it will focus more on the application. And also we are also now trying to make SiXCY materials so that you can tune the properties. For example, not only you can make a blue LED, you can make it green, yellow, whatever, just by changing the composition between silicon and carbon. Yes, that is for future patent.
Thank you. Lisa, back to you.
Thank you, everyone. It's a great discussion here. And thank you, Sakineh, for your presentation and answering the questions. We will take a short break and come back, let's say right after 10:15, just a very short break for our next segment, which will be moderated by my colleague, Matt O'Brien from AFRL. Thank you.